a crate of mass 7.4 kilograms, so this is our crate, is pushed against a box of mass 3.3 kilograms, so this is the box, by a horizontal force of 13.4 newtons to the right as shown. If the surface is frictionless, find the acceleration of the box in meters per second squared. So push this off to the side. So let's do some free body diagrams. For the crate, I have some weight downward, which we'll call FGC, and some normal force, which I'll call FNC. And it's being pushed, which I'll call FP. And then for the box, I'll have a weight, which I call FGB, because it's different. And I'll have a normal force, which I'll call FNB, because it will generally be different. And now I have to be interested, because I have to be careful, because the crate is trying to push into the box. So there'll be some force here, which I'm just going to call F1 for the moment. It's itself probably a normal force. I'm pushing in. But that means the force that the box resists, and so there's a force pushing back like this. And I can use the same F1 because Newton's third law tells me that if the crate is pushing on the box, then the box is pushing back on the crate at the same strength. For both of these things, then the box will have some acceleration, which I'm going to call A sub 1. And since the crate doesn't go through the box, it will have the same acceleration. It will push the box over and they'll stay together. So I'll have the same acceleration. So in the Newtonian recipe, this was step 2. Step 3 says any constituent equations, and really there's only going to be one of them, although I guess it's a little duplicate. The weight of the crate is mc times g, and the weight of the box is its mass times g. All right. Then step 4 says, from our diagram, what are the F nets? So, and here we're going to have really, we would have 4, a vertical and horizontal for each. But we also know that since there is no friction here, there's nothing connecting the normal force to the horizontal forces at all. So I'm going to leave them out. We just know that the normal force of C equals the weight of C, and FNB equals the weight of B, but they don't tell us anything. So now I'm just going to worry about the crate's horizontal forces and the box's horizontal forces. From the crate, we look up here and we say, well, I'm pushing one way and I'm feeling a push back from the other. So I can say something like, this is FP, and there's an F1, and then there's a sign between them that is like that. And then looking at box on the box, we have just F1 pushing, so I'm just going to say F1. And step 5 says write equations for the accelerations. So we have A of the crate is something, and A of the box is the same something. And what we're looking for now is, this is what we're calling A1, the acceleration of the box. Turns out to also be the acceleration of the crate. Wasn't asked for that. Step 6 says, remember that every F net is the mass times the acceleration. And so on the crate, that's true, and on the box, that's true. Oops. And finally, step 7, not finally, but step 7 says put these things together. So we're going to take, for F net, we're going to take this and plug it in down there. And we're going to end up with F net, sorry, not F net, but rather FP minus F1 equals the mass of the crate times A1. And then we're going to have also that F1 equals the mass of the box times A1. And that came from taking this and plugging it down there. And we look and we say, well, what do we know, what do we not know? I'm going to highlight the things that we don't know. Well, we were told the pushing force, but we don't know F1. Oops. We do know the mass of the crate, but we don't know A1. And so what we have here are two equations and two unknowns. So step 8 says solve, but they're kind of annoying, but not too bad. All right, we want to solve it somehow. The way I'm going to solve it is I'm actually going to add the equations. So when I take, all right, I'm just going to recopy them. I have FP minus F1 equals MC AC, and I have just F1 equals MB AC. So when I do the additions, when I say just add this equation to the other equation, well, FP just comes along, and then something kind of magical happens, which is that minus F1 plus F1, those go away. And I'm left with MC A1, these should be A1s, plus MB A1, which I would certainly factor out. And that lets me divide over, and I would find, I'm gonna move over here just to not have to scroll again, that A1 will equal the force with which we push over the sums of the masses. So pulling our numbers out, 13.4 newtons over 7.4 kilograms and 3.3 kilograms, which is 1.25 meters per second squared. By the way, you could look at this whole problem and say, hey, since they slide off together, couldn't I have just treated them as one 10.7 mass object and then just taken the force on that, which is 13.4, and divide by the mass, which is 10.7? Yeah, we'd end up in the same way. We have accidentally proven that because the F1 part went away. It was internal to those two things, so if we consider them as one object moving with one acceleration, then we could have just done that quickly. And if you had done that, you're perfectly fine. Don't feel like you should have done it this way. But we'll see in a second that this, in the next problem, it's nice to have done it this way. Follow-up problem. A crate of mass 7.4 kilograms pushed against a box of mass 3.3 kilograms by a horizontal force of 13.4 newtons to the right is shown. Same setup. But if the surface is frictionless, find the force in newtons that the box exerts on the crate. And again, just to remind you, the setup that I had done before, we had FGC and FNC. Those are from the floor. We were pushing, but there was a back force F1. That is the normal force coming from the box when it's resisting being pierced. Of course, by Newton's third law, that means that we must be pushing on the box, which of course we were. FGB, FNB, and we know that there is accelerations this way, which we just found were 1.25 meters per second squared. So what we're looking for is the force that the box exerts on the crate. That is clearly this force. And that's annoying. But it equals this force. So if we remember, we had F net of the box in the x is the mass of the box times its acceleration. And from the diagram, that's just F1. And then over here, we would have 3.3 kilograms. And here we have 1.25 meters per second squared. So that's 3.3 times 1.25, 4.125, and of course newtons. That's the answer. If we look at the net force on the crate, well, the net force on the crate would be the pushing force of 13.4 newtons minus this 4.125. So the net force is 9.275. And if we say, hey, we take that 9.275 and divide by the 7.4 kilograms, we get, as we should, the same 1.25 meters per second square acceleration. In other words, F1 is big enough to accelerate the box, but also to slow down the crate enough that they end up having the same acceleration. Same situation, but imagine now that the force is applied to the box instead of to the crate. If the surface remains frictionless, is the force of the box on the crate larger than what we just found, or the same, or less? So is it larger or smaller than the 4.125 newtons that we had just found? And to get to the answer first, it will be a larger force. And you're like, huh, that's weird. But remember, let's look at our free body diagrams one last time. So now we're going to say these two forces, and we'll still have the same weights because we haven't changed anything there. And we'll have the same normals from the table because we haven't changed anything there. Right? We haven't changed any vertical stuff, so that can't change. Now we're pushing from the right with FP. And I'm going to give them a different name. I'm going to say, well, then we push on this with what I'm going to call F2, which means it pushes back with F2. And our question is whether this F2 is equal to, greater than, or less than the F1. Do remember, of course, that there is still an acceleration. And here I'm going to use something we got in the first problem. And I'm going to say, oh, wait, but it's the same net force on the same combined object, so it still has to be the 1.25 meters per second square. And now we're going to say, well, how about the net force on the crate in the x? I'm going to choose this now to be my positive direction. So I'm going to get just F2. Of course, the second law is always equal to the mass of the crate times its acceleration. And so even without getting numbers, since F1 was the mass of the box times the acceleration, and F2 is the mass of the crate times the acceleration, and the crate has a larger mass, it must also have the larger force. So to get that formally, then F2 equals the mass of the crate times the acceleration, which is 7.4 kilograms times 1.25 meters per second square. And that's going to be about 9.25 newtons. In other words, the same net force as before, which is what it would need to be. But a larger, the box is pushing back harder. Why? Because now the box has to push the crate out of the way, and that takes more force. Because of that, the effect of the pushing force on the box is reduced, because that means the crate is pushing back at a higher rate than it would have been before.